Figure shown below shows a circular wire loop of radius A carrying a current I placed in a perpendicular magnetic field B. Consider a small part dl of the wire. Find the force on this part of the wire exerted by the magnetic field, and then find the force of compression in the wire. So if we consider this particular arrangement where the current is carrying in the anti-clockwise sense and the wire is placed in a magnetic field B which is directed inwards. So I am redrawing this in a bigger way. So we have a setup like this. So over here the current is carrying in the counterclockwise direction, that is something like this, and the radius is A, the magnetic field is B, which is directed into the plane of the paper. So now we are considering a small portion dl. So let us consider a small portion over here as dl of the wire, and then we are drawing it with the center something like this. So we consider a small portion dl segment of this wire, and now I can say that the force which is going to act on this is going to be equal to a small force, that is df, which is going to be I dl cross b, and hence from here we obtain df as equal to I dlb. So this is going to be the answer for the first part, that is I dlb. So now we are going for the solving the second part. So now the question is stating that find the force of compression in the wire. So what we are seeing is, if we find out the direction of this force, then it is directed inward. So over here at the 2 points, if I draw a tangent something like this, and then I draw a tangent something like this, so this is going to be the response for the value of tensional force that is generated. And if this is going to be the response, so we are considering or breaking this line which is drawn from the center like this. So we are considering that this each angle is going to be equal to theta, that is the dl segment is subtending an angle of 2 theta. Now since this is projected at 90 degrees, so we tangent is drawn, so we consider these two angle as 90 and 90, and now if I draw a line parallel to this, so I can say that these angle is also become equaling to theta, and this one is also equal to theta. So that is I can say that 2t sine theta will be responsible for balancing the force which is IDLB, and hence I can say that if the theta is very small, so I can write it as 2t, and then the theta can be written as arc length, which is equal to dl by 2, and radius r, which is equal to IDLB. So from here we obtain the force of compression as equal to T is equal to IRB. Now since the radius is equal to A in this problem, so we write it as IAB. So this is going to be the answer for the B part. A current is I is passed through a silver strip of width D and area of cross section A. The number of free electrons per unit volume is n. Find the drift velocity of the electrons. If a magnetic field B exists in the region as shown in the figure given below, what is the average magnetic force on the free electrons? The next part is, due to the magnetic force, the free electrons gets accumulated on one side of the conductor along its length. This produces a transverse electric field in the conductor which opposes the magnetic force on the electrons. Find the magnitude of the electric field which will stop further accumulation of electrons. And the next part is, what will be the potential difference developed across the width of the conductor due to the electron accumulation? The appearance of a transverse EMF when the current carrying wire is placed in the magnetic field is regarded as Hall effect. So we are reading with about Hall effect over here. So this can be treated as a paragraph on Hall effect. So if we start approaching this problem, so the first thing which we say, that if a wire is carrying a current I, having the charge per unit volume, that is free electrons per unit volume, or carrier charge density as a small n, cross sectional area A, and we already know the electronic charge. So from the equation that is I is equal to Q N A V, or we can write it as NEAV, we can calculate the value of drift velocity, that is the drift velocity is equal to I upon NEA. So this is going to be the answer for first part. So the expression, this expression is obtained in the current electricity chapter, and then from there we are obtaining the value of drift velocity which is equal to I upon NEA. Now the question is asking what is the magnetic force which is acting on it. So if we calculate the value of magnetic force on the electron, so we can say that the force on a charged particle can be written as F vector is equal to E V cross B. Now since it is an electron, so we are putting a negative sign over here. So if we calculate this force, so we can write it as E, the value of V which is equal to I upon NEA, and B. So we cancel this out and we obtain the value of force as IB upon NA. So if we look at the direction, so let us look at the direction in which this force is acting. So since the carrying the current is going from left to right, so I can say that the electron is moving from left to right, something like this, and electron is negatively charged particle. Now the magnetic field is present perpendicularly inward, that is directed into the plane of the screen, and this is the velocity v. So if we calculate the direction for v cross b, then it will be in the downward direction. Now since the direction of force will also depend upon the nature of charge, which is negative charge, so when we do v cross b, we obtain the direction in the downward direction. But since the charge is that of an electron, which is a negative charge, so I say that the electron will move upward. So I write over here upward. So this is how we deal with it. There is also one more possibility by which you can do it. You can directly use Fleming's left hand rule, and using Fleming's left hand rule we can consider it this way, that your index finger is pointing into the plane of the screen, the middle finger is pointing towards the direction of current, that is towards the right, and you will find that your thumb is pointing in the upward direction. So the direction of force is again in the upward direction. So as a result of which this force IB upon NA is directed in the upward direction. Now the next part, the question is saying, due to the electron accumulation on one side of the conductor along its length, a transverse electric field in the current is produced which opposes the magnetic force on the electron, thereby the accumulation further stop. So when the accumulation further stop, I mean to say that the deflection of charged particle is prevented because of the presence of magnetic and electric field both. That is, we can write an expression like this, that if a charged particle is placed in an electric and magnetic field simultaneously, so a force which is going to act on it is E vector plus V cross B. So if there is no accumulation, then I can say that the F net acting on the particle is 0, and hence I can say that E plus VB is equal to 0, or we can calculate from here that the magnitude of V is equal to E by B. So we can write an expression like this. This expression is also applicable in the concept of velocity separator device. So over here we can use this expression that the magnitude of V is equal to E by B, and now over here we are writing if the electric field E is developed. So we can write it in this way, that the value is going to be equal to the velocity. So the velocity value is I upon NEA, I upon NEA. So the value of electric field that must be developed is calculated as I is equal to IB upon NEA. So this is going to be the value of the transverse electric field that will be created in order to prevent further accumulation of electron. In the next part, the question is asking what will be the potential difference developed across the width of the conductor due to the electron accumulation. So now the question is asking us to find out potential difference. So we can easily do it once we have the value of electric field. So I can write the value of potential difference dV is equal to E dot dr, or the value over here is simply going to be multiplied with d. So we can calculate the value of potential difference simply by using this. V is equal to Ed. So the potential difference will come out to be IBD upon NEA. So this is the required answer for this particular problem. A narrow beam of singly charged carbon ions moving at a constant velocity 6 into 10 to the power 4 meter per second is sent perpendicularly in a rectangular region having uniform magnetic field B equals 0.5 Tesla. The figure is given below. It is found that the two beams emerge from the field in the backward direction. The separation from the incident beam being 3 cm and 3.5 cm. Identify the isotopes present in the ion beam, taking the mass of the ion A as 1.6 A into 1.6 into 10 to the power minus 27 kg, where A is its mass number. So if we consider this kind of a problem, so over here the first thing that we will be doing is we will be calculating the radius of each particle which it is going through. So since the value of every parameter, that is the velocity, magnetic field, is same, so we can easily calculate the ratio. So if I redraw this loop, or the path in which they are going, so the path is in somewhat this way. So this is the common entry point into the magnetic field, and the two particle is split because of the variable force which is acting on them, perhaps because of the mass which is being mentioned over here. So this is going to be the diameter of the first particle d1, and this is the diameter of the second particle which is equal to d2. So I can say that diameter d1 is equal to 3 centimeter, and the diameter d2 is equal to 3.5. So I can take this ratio as 6 by 7, which is also going to be the ratio for R1 and R2. Now if we consider this particular problem, so we are finding that the velocity, magnetic field, which are the other two parameters apart from mass, is same for both. So if I use the expression R equals mv by qb, so it is saying that a singly charged carbon ion, so the value of charge is also same. So we say that all these three parameters which governs the velocity, which governs the value of radius, is same. That is V upon QB is same for R1 and R2 both. So I can say that R1 by R2 is equal to M1 by M2, where M1 and M2 are the masses of the two isotopes respectively. So from here I can say that the radius r1 by r2 is equal to m1 by m2, which is equal to 6 by 7. Now from here it is all about common sense that we know that for carbon the two isotopes which we can see over here are basically in the ratio 12 and 14, that is 6C12 and 6C14 are the two isotopes which the problem is talking about. Since the ratio is 6 by 7 and we are calculating the mass number for carbon which is also mentioned, so now I can say that it is equal to 6C12 and 6C14 respectively. So let us move to the next problem. So in the next problem the question is stating two particles each having a mass m are placed at a separation d in a uniform magnetic field B as shown in the given figure. They have opposite charges of equal magnitude q. At time t equal to 0, the particles are projected towards each other with a speed v. Suppose the Coulomb force between the charges is switched off. So this is an interesting point which must be kept in mind, that the Coulomb force between the charges is switched off. Find the maximum value Vm of the projection speed so that the two particles do not collide. In the next part the question is stating what should be the minimum and maximum separation between the particle if the above calculated velocity is reduced to half. And then the next one is at what instant will the collision occur between the particle if v is equal to twice of vm. And then the last part the problem is saying suppose v is equal to twice of vm and the collision between the particles is completely inelastic, so we have to describe the motion after the collision. So it is a very interesting problem that we are going to deal with. So the first few things which must be kept in mind, that the two particles are having the same speed and the magnitude of charge is same, but the direction is different. So now over here one thing is for sure true, that if we see the direction of the positive charge, so the positive charge will move in the upward direction because of the velocity and the direction of magnetic field which we have, that is the positive charge is going to move in a path like this, in the upward path. And if I talk about the negatively charged particle which is approaching from the other direction in the same magnetic field, so this negatively charged particle is going to move in this direction, and this is the reason that there is a tendency for them to collide. So the first thing that we wish to know is this part, that what is going to be the direction of the motion of each charged particle. So now the first part is asking find the maximum value Vm of the projection speed so that the two particles do not collide. So since as I mentioned over here that the value of charge, velocity and the value of masses is same for both the charged particle, so I can say that they both will move in the same radius r equals mv by qb, and their motion is governed by the direction which we have already determined. So in order to prevent the collision, so I am drawing one more diagram. So in order to prevent the collision, this is the possibility which we can think of, that as the charged particle is moving, so it will move out like this, the positive charged particle, and the negatively charged particle which will start from the other end will move out like this, such that they just brushes against each other. And we are saying that this separation is given to us as d. So the value of radius in which this charged particle is moving is d by 2, and for the other one is also d by 2. That is we can say that the value of r is equal to d by 2 and can be equated to mv by qb. So if we equate this to mv by qb, so we can calculate from here the required velocity, which can be written as qbd by 2m. So this is the answer to first part, where the problem is asking us to calculate the maximum value Vm of the projection speed so that the two particles do not collide. Now in the next part, the question is saying what would be the minimum and maximum separation between the particles if the speed is reduced to half. So if we reduce the speed to half, so the value of radius which we saw over here was d by 2, and we have seen that m by qb remains the same. So if I reduce the velocity to half the value, that is Vm by 2, so this is also going to reduce by 2. That is it is going to move in the radius which is equal to d by 4. So for the B part, this is the calculation which we have done, that if we reduce the velocity to v by 2, so the radius is going to become d by 4. Or you can also cross check from this result that if we use the velocity equation v by 2, then we can calculate radius for B part over here again using the velocity v by 2. So the value of radius can be calculated as mu radius, which is equal to m. So velocity is half of the current value, that is 4m by qb. So from here we obtain the same result, that is d by 4. So now if the charged particle is moving in the radius of d by 4, so if we consider another diagram, so I am saying that the charged particle is moving in a radius of d by 4, and this was the starting point, and the negatively charged particle is moving in a radius of d by 4, and this was the starting point. So this is the point of minimum separation. So this is going to be the point of minimum separation, d minimum, and this is going to be the point of maximum separation, that is I am writing with capital D, d maximum. Now the problem is telling us that the initial separation between them is small d, and the radius in which it is moving is equal to d by 4. So we are taking this distance as d by 4, and this distance as d by 4, and hence I can say that the minimum distance between them will be this parameter, that is equal to x. So from here I can write that d by 4 plus x plus d by 4 must be equated to d, that is this is equal to d by 2, so x is equal to d by 2. So d minimum, or the minimum separation between them, will be d by 2. And if I calculate the maximum separation, so we already know the center to center distance, which is equal to d. We only need to add these parameters, that is d by 4 on both sides. So we get the maximum distance as small d plus twice of d by 4. So from here we obtain the value equal to 3d by 2. So for this problem we have solved the B part as well. Now if we come to the last part, at what instant will a collision occur when the particle speed is equal to twice Vm? So if the particle speed is equal to twice Vm, so what is to be done is that we are trying to calculate the value of time when the collision will take place. So in order to collision to take place, both the particles must cover equal distances. So if both the particles are covering equal distance from here, so we are saying that the velocity is twice of Vm. So if we approach this problem like this, so if the problem, this was B part, now we are dealing with C part. We are saying that the velocity is equal to twice of Vm. So Vm is calculated by us as qbd by 2m. So if I put the value over here, so we get twice of qbd by 2m, that is the expression will reduce to qbd by m. So this is the value of velocity which we have, that is twice the value of velocity. So if we consider that the collision take place for this will be r is equal to mv by qb. So this is the next radius which we are calculating. So I am calling it as r3, that is m by qb into qbd by m. That is they are moving in a radius equal to d. So now what will happen, as the charged particle move, it will move something like this. This is the trajectory of the positive charge particle plus q, which is moving with twice Vm. and the other one, which is the minus q and is also moving with twice Vm, will follow a trajectory like this and it will collide somewhere here. So the collision will happen at this point where the initial separation between them was equal to d. So each of them is a part of circle whose radius is equal to d, and they are colliding at the midpoint, that is d by 2. That is d by 2. So they are colliding at d by 2 mark. So if I draw this in the form of a circle, so it will be better for us to understand that we are considering that the particle was moving like this in a circle with a radius equal to d, and the collision take place when it moved this distance, which is equal to d by 2. So this distance is equal to d by 2, which we have. So if we calculate the angle which it have moved, so this is the angle which we are looking for. So if we calculate this angle, we can calculate using sine, that is sine theta is equal to d by 2d. So the value is equal to half, that is it have moved an angle of 30 degree. So we can say that it have moved an angle of 30 degree or pi by 6. So the question is asking us to calculate the time taken for the collision to take place. Let us come back to the question. So the question is at what instant will the collision occur? So since we know that the total time of the circular path is 2 pi m by qb, so in order to move this distance pi by 6, so we can say that for moving 2 pi, the time taken is 2 pi m by qb. So in order to move pi by 6, the time is going to be pi by 6 m by qb. So this is the time after which the collision will take place. That is pi by 6 m by qb. Now let us deal with the fourth part of this problem. So if we deal with the fourth part of this problem, the problem is stating suppose V is equal to twice Vm and the collision between the particle is completely inelastic. Describe the motion after the collision. So this one is a much simpler problem in comparison to the above three problems. So the problem is saying that the collision which takes place over here is completely inelastic. So even if the collision is completely inelastic, we say that the momentum along x-axis will be conserved. So if the momentum is conserved along x-axis, I say that initially the particle was having the same component of velocity along the x-axis, and hence the velocity component along the x-axis will cancel each other out and the particle will move in the straight line along the y-axis. So if we describe the motion, so the motion of the particle will be that the particle will stick together and the combined mass will move with a common speed along the straight line, which can be drawn upward in the plane of the figure like this from the point of collision. So with this we can move to the next problem. Two long straight parallel wires are 2 meters apart perpendicular to the plane of the paper, which is shown in the diagram. So we have a wire A and a wire B. The wire A carries a current of 9.6 amperes directed into the plane of the paper. The wire B carries a current such that the magnetic field of induction at the point P at a distance 10 by 11 meter from the wire B is 0. Find the magnitude and direction of the current in B, the magnitude of the magnetic field of induction at the point S, the force per unit length on the wire B. So for solving this problem, we will be using these working formula. So the magnetic field due to infinitely large wire is written as mu naught I upon 2 pi r. So we can rearrange the term to write this equation in this way as well, mu naught upon 4 pi into 2 I by r. So we do this kind of a modification just to make sure that from mu naught, that is 4 pi into 10 to the power minus 7, we can directly cancel 4 pi. So we write equation in this fashion as well. And the value of force per unit length can be written as mu naught I1 I2 upon 2 pi r, where I1 I2 are the current in the long straight wires and r is the perpendicular distance between the two wires. So this is these are the two working formula which we will be using to solve this particular problem. So let us begin by first of all finding out the direction of magnetic field due to the current carrying wire in A. So since the current is carried in the inward direction, which is designated by cross over here, so I can say if we place our right hand thumb into the screen at point A, then the right hand palm will be directing us in this direction. So I am calling it as PM. So it will be directing us in this direction. So now in order to nullify the result of this magnetic field, it is important that the wire B must be carrying current in the upward direction so as to cancel the magnetic field due to A at P, and hence I am calling it as maybe it will produce a PQ magnetic field in this direction whose vector is represented by PQ vector. So if I start solving it out, so let us begin by calculation of magnetic field at P. So we are finding out magnetic field at P. So the first thing which we are doing is we are calculating magnetic field due to A. So due to A we write it as mu naught upon 4 pi twice of current in A upon distance AP. So this is current in A and distance AP. So if I put the value, I can write it as mu naught upon 4 pi twice of current in A is 9.6 and the distance is 2 plus 10 by 11. So this is the value of magnetic field over here due to A. Now what we are doing is we will be calculating magnetic field due to B, which is opposite to the direction of the magnetic field which is produced by A at point P. So for B I am writing it as mu naught upon 4 pi twice of current in B upon distance, which is 10 by 11. So now from both these equations I can say for the magnetic field to be 0 at point P, it is necessary that magnetic field due to A must be cancelled out magnetic field due to B. So we can solve it out like this. So mu naught upon 4 pi term is common, 2 is common, so I can write it as 9.6 upon 2 plus 10 by 11 is equal to IB upon 10 by 11. So we obtain equation like this, and from here we obtain that the current flowing in the wire B is equal to 3 ampere and it is coming out of the plane of the screen. So IB is equal to 3 ampere. Now let us move back to this diagram. So in this diagram, the next question that is asked is the magnitude of the magnetic field of induction at the point S. So if we consider the dimensions, so I can say that the dimensions are of an of a right angle triangle. So if the dimensions is of a right angle triangle, and we can clearly find out that angle ASB is equal to 90 degree. So it is a Pythagoras triplet, and angle ASB is equal to 90 degree. So for this particular part, we can write it as SA square plus SB square is equal to AB square. So it is clear from this triangle that it is a right angle triangle. So if we calculate magnetic field due to A at S, then it will be directed from S to B. So I can say that it will be directed from S to B like this. S to B. It is magnetic field due to A. So I am writing it as BSA. Magnetic field at a point S due to A. And magnetic field due to B at S will be directed from S to A. And both the direction is determined using Maxwell's right hand rule. So I am writing it as BSB. Magnetic field at S due to B. So these two are perpendicular to each other. So if we do our necessary calculation over here, so I can say that we are solving the next part. So magnetic field at S due to A can be written as mu naught upon 4 pi twice of current in A by the distance, that is RSA. So we can write this as mu naught upon 4 pi twice of 9.6 upon the distance, which is equal to 1.6, and the direction we have already discussed, directed from S to B. Now we are calculating magnetic field at S due to B. So we write it as mu naught upon 4 pi twice of current in B upon RSB. So if we do this, we write it as mu naught upon 4 pi, so twice of the current, that is 3 ampere, upon the distance, which is equal to 1.2, and the direction is already discussed by us, it is directed from S to A. Now since both these magnetic field are perpendicular to each other, so I say that BSA and BSB are perpendicular to each other, and hence I can write the net magnetic field can be written as mu naught upon 4 pi, and then we will square the term and add them, that is 9.6 upon 0.8 whole square plus 3 upon 0.6 whole square. So we are basically doing vector addition, root over a square plus b square. Since the term mu naught upon 4 pi was common to both, we took it out, and on calculation we obtain a value equal to 1.3 multiplied by 10 to the power minus 6 Tesla. So magnetic field at a point S is 1.3 into 10 to the power minus 6 Tesla. Now in the next part, the question is asking us to calculate the force per unit length on the wire B. So for this part, we are saying that the force per unit length on the wire B, that is the third part. So I already specified the working formula, that force per unit length is written as mu naught I1 I2 upon 2 pi r. So if we do the calculation, we can write it as, so I am writing it as 10 to the power minus 7 into 2 into 9.6 into 3 by 2. So I have modified this expression by multiplying 2 on both sides. So from 4 pi we can cancel out mu naught and obtain 10 to the power minus 7, and on solving we obtain it as 28.8 into 10 to the power minus 7 Newton per meter. And it is important to mention over here that the force will be repulsive in nature because they are carrying current in the opposite direction. So the force is of repulsive nature. Let us move to the next problem. A pair of stationary and infinitely long bent wires are placed in the xy plane as shown. The wires carry current of I equal to 10 amperes each as shown. The segments L and M are along the x-axis. The segment P and Q are parallel to the y-axis. So this one is L and M, and this one is P and Q, such that OS equal to OR equal to 0.02 meter. Find the magnitude and direction of the magnetic induction at the origin O. So we are saying that the wires are representing semi-infinitely large wire. So if these are semi-infinitely large wires, so magnetic field due to semi-infinitely large wire is written as mu naught I upon 4 pi r. So we write it in this form of an expression, mu naught I upon 4 pi r. So this will be our working formula. So magnetic field due to current carrying conductor P at point O can be calculated. So we are saying magnetic field at a point O due to P. So we are writing it as mu naught upon 4 pi, the current which it is carrying upon distance, which is equal to OR. So we write it as mu naught I upon 4 pi and the distance that is equal to OR, and it is directed outside the plane of the screen. So the magnetic field will be directed outside the plane of the screen. So we can place our right hand thumb in the direction of the current carrying wire, and over here we will find out that the magnetic field is pointing outside the plane of the screen. And similarly, if we are writing the equation for the current carrying conductor Q, so the magnetic field due to Q can be written as mu naught upon 4 pi, the current which it is carrying, and the distance which is equal to OS. So this is also directed perpendicular to the screen, and it is towards us again. So again we can do the same sort of thing. We can place our right hand thumb in the direction of current carrying wire, and the palm will be pointing towards us at point O. So hence we can say that the net magnetic field will be sum of these two, that is magnetic field due to P and magnetic field due to Q can be added together, and we can write it as mu naught I upon 4 pi 1 by OR plus 1 by OS. And if we put the values, we obtain it as 10 to the power minus 7 into the current, and then we are left with 1 upon 0.02 plus 1 upon 0.02. So we will obtain a value of 10 to the power minus 4 Tesla. So over here it is equally important for you to understand that there will be no contribution in magnetic field due to L and M. They will not produce any magnetic field at the point O. So we are not taking that into consideration. Let us move to the next problem. Let us begin with the third problem. A wire loop carrying a current I is placed in the xy plane as shown in the figure. If a particle with charge plus q and mass m is placed at the center P and given a velocity v vector along np, then find its instantaneous acceleration. If an external uniform magnetic induction field B vector is equal to B I cap is applied, find the force and the torque acting on the loop due to this field. So if we consider this particular problem, we can begin by the calculation of magnetic field at the center. So if we look at this segment, then there is an arc Mn which is producing a magnetic field at P, and a straight wire Mn which is producing a magnetic field at P. So if we begin by the calculation of magnetic field due to them, so we are calculating it in this way. Let us begin with the calculation of magnetic field due to arc. Magnetic field due to arc Mn. So due to arc, magnetic field is given as mu naught Ni upon 4 pi r alpha. So for this particular problem, the value of alpha is 120 degree, or we can say 2 pi by 3. So we write it as mu naught I upon 4 pi. The radius is given to us as a into 2 pi by 3. So if we consider this, we can simply write it in this fashion. The way it is, we will simplify it later on. So we are calling it as b1 vector. If we calculate the direction of b1 vector, then it is directed outside the plane of paper or the screen, and hence we call it as plus k cap. The next thing which we are looking at is magnetic field due to current carrying straight wire. So if we look at this formulation, then if there is a current carrying straight wire I, and a point over here is subtending angle alpha and beta, which is at a distance r. So we can write it as that B is equal to mu naught I upon 4 pi r sine alpha plus sine beta. So if we consider this aspect of the problem, so we can say that for this particular wire over here, the angle which is subtended is 60 degree, and if this is A, the distance r can be written as A cos 60 degree, which is equal to A by 2, and hence we can calculate the value of magnetic field as mu naught upon 4 pi I upon A by 2 sine 60 plus sine 60, that is twice of root 3 by 2. So if we look at this aspect, so we find out that the magnetic field due to the current carrying straight wire Mn is directed into the plane of the screen, and hence we assign a minus k cap direction to this magnetic field, which we call as B2 vector. So after the calculation of both the magnetic field, we calculate the value of net magnetic field. So the net magnetic field can be calculated as the vector sum of B1 and B2. So if we do the vector sum, we will obtain mu naught I upon 4 pi A 2 by 3 minus 2 root 3 k cap, which on simplification is obtained as minus mu naught upon 4 pi 2 I by A into 1.4 k cap. So this is the value of magnetic field that we obtain at the point P. Now in order to calculate the force on the charge q and mass m, which is placed at the center P and given a velocity along np, so we are breaking the component of velocity. So the velocity is directed in the direction of np, so I can say that it is making an angle of 60 degree with the x-axis, and hence we can say that the velocity vector of the particle is equal to v cos 60 degree I cap plus v sin 60 degree j cap, and the value is written in terms of v by 2 I cap plus root 3 by 2 v j cap. So this is the value which we obtain for the velocity vector, and hence the force vector which is acting on the particle can be written as q v cross b. So if we use this expression over here, so we can write it as capital Q, and v cross b can be written as v by 2 I cap plus root 3 by 2 v j cap cross the magnetic field value, which is equal to mu naught upon 4 pi 2 I by A into 1.4 k cap. So if we put this value, and then I can say that the value of acceleration which the question is asking us can be calculated by equating this value with F equal to ma. So if we divide this expression by m, so we will obtain the value for acceleration, and hence I can write it in this way, that the value of acceleration can be written as A is equal to F by m, and hence the value is written as Q by m times of this expression, which we will solve and obtain it as equal to 0.11 times of mu naught IV upon radius a. So this is the radius a which we are taking, not the value of acceleration, so I'm denoting acceleration with a naught. So this becomes the instantaneous value of acceleration, which is directed 30 degree with the negative x-axis. So this is the value of instantaneous acceleration for this particle. So if we look at the next problem, the question is asking if an external uniform magnetic field B vector equal to B I cap is applied, find the force and the torque acting on the loop due to this field. So the first thing which I can say for the B part is that any loop placed in any closed loop placed in a uniform magnetic field experiences no force, experiences no force. So the force acting on the loop due to the externally applied magnetic field is zero. Now the next part, the question is asking us about the torque acting on the loop in the magnetic field. So the value of external torque is written by the expression m cross b, where m is written as INA vector. So if we write it in this fashion, so let us begin by the calculation of area vector. So if we begin with the calculation of area vector, so the area for this patch is going to be this area which is enclosed by this particular minor secant. So if we wish to calculate this area, then we need to subtract the area of sector MPN with the triangle MPN. So if we do this calculation, so we can say that the area is equal to 1 by 3 times of pi a square, because it is subtending an angle of 120 degree, minus half of mn into ps, so which is basically half into base into height, so which is equal to root 3a and a by 2. So I already calculated those two values while solving for the magnetic field part. So I can put this value and obtain it as pi a square by 3 minus half of root 3a into a by 2. So we will obtain an expression like this, which on simplification will give us an area a square pi by 3 minus root 3 by 4. So this is the value of area we have. Now for the direction of m vector, or hence the direction of area vector, we specify the direction using the right hand curl. So the rule says we curl our right hand in the direction of flow of current and our thumb will give us the direction. So if we curl our right hand in the direction of current, so it is curling like this, and my thumb is pointing outside the plane of the screen, and hence I say that the value of m vector is directed along k cap. So I say that it is assigned a value along k cap. So now I can write the value of tau vector, which is given by INAB. So if I multiply INAB, since the number of turns is equal to 1, so we simply obtain a square pi by 3 minus root 3 by 4 k cap cross magnetic field which is directed along I cap direction. So on solving this, we obtain the torque vector, that is obtained as BIA square pi by 3 minus root 3 by 4 j cap, which is equal to 0.614 BIA square j cap. So this is the final answer for the uh, third question which we have solved. So this one is the part B second answer. This one was part B first answer where the question on the loop was asked, and this was the instantaneous value of acceleration for a charge that is placed in front of the loop. Let us deal with the next problem. A circular loop of radius r is bent along a diameter and given a shape as shown in the figure. One of the semicircles K and M lies in the xz plane and the other one KLM in the yz plane with their centers at the origin. Current I, Ampere, flowing through each of the semicircles is as shown in the figure. A particle of charge q is released from origin with velocity v vector is equal to minus v naught I cap. We have to find the instantaneous force on the particle. Assume that the space is gravity free. The B part, the question is asking if an external uniform magnetic field B vector equal to B naught J cap is applied, then determine the force F1 vector and F2 vector on the semicircles KLM and KNM due to the field and the net force F vector on the loop. So if we begin solving this problem, so the first thing that we will be calculating is the magnetic field at origin. So we begin by the calculation of magnetic field in the origin. So these two semicircular loops are there. So I again write the value of magnetic field due to an current carrying arc, which is written as magnitude of B is obtained as B is equal to mu naught Ni upon 4 pi r into alpha. Now since in this case each wire is having a single turn and they are subtending an angle of pi, so I can say that the magnitude of magnetic field due to each of them is going to be mu naught I upon 4r. So this is going to be the magnitude of magnetic field due to each of them. Now if I look at the direction parameter, so I can say that due to KLM, the direction of magnetic field is along the negative x direction. This is along the negative x direction, and due to KNM, the direction is along the positive y direction, that is along j cap. So it is simply determined by using right hand rule. So if you place your thumb in the direction of current carrying wire, then your palm will give us the direction of magnetic field, and hence we can say that in the vector form we can write a B vector as mu naught I upon 4r minus I cap plus j cap. So this is the value of magnetic field due to the two loops KLM and KNM respectively. Now the question is saying that a particle of charge q is released at the origin and is having a velocity minus v naught I cap. So if we calculate the value of force on this particle, then the value of force is given by F vector is equal to q v cross b. So we have the velocity and magnetic field both in the vector form. So we can calculate by just putting the value q. V vector is equal to minus v naught I cap cross of the value of magnetic field, which is equal to mu naught I upon 4r minus I cap plus j cap. So this is the value of the force that we obtain, and on doing the cross product we obtain a value equal to minus mu naught q v naught I upon 4r, which is directed along negative z-axis direction, that is minus k cap. So we have this expression over here for the value of instantaneous force on a charged particle which is moving along the negative x-axis direction. In the next part, the question is asking if an external uniform magnetic field B naught j cap is applied, then determine the force F1 vector and F2 vector on the semicircle KLM and KNM due to the field and the net force on the loop. So for this particular problem, we can say that the magnitude of force is determined using the expression F vector is equal to I L cross B. So we can also determine the direction of force by solving this portion or by using Fleming's left hand rule. So the question is saying that the applied value of magnetic field is in the B naught j cap direction. So we have to determine the force F1 vector and F2 vector on the semicircles KLM and KNM. So in case of an irregular shaped conductor placed in the magnetic field, we use the length as the shortest distance between the two ends of the conductor. And hence, I can write that the force vector on Km can be written as Vi into 2R. And if we use the Fleming's left hand rule, we will obtain that the direction of force is along the I cap direction, which is equal to 2BIR I cap. And the value of force which is acting on the loops, that is KLM and KNM, is going to be same, and it can simply be calculated by calculating force on Km, which we have obtained as 2BIR in the I cap direction. So and hence therefore the total force acting on the loop will be sum of the forces, since both the force is same. So we just double the value to obtain the net force as 4 times of BIR in the I cap direction. So with this we solve this particular problem, which was asking us to calculate the instantaneous force acting on the particle and the force on the loop when the externally applied magnetic field is applied. So now you can have a contradiction with the previous problem where I said that the net force acting on a loop placed in a uniform magnetic field is 0, but over here the loop is carrying current in the opposite direction. So if it would be a single loop, so this would be carrying current like this from here to here and then from here to here. But the two are carrying current in the opposite sense, and hence the forces are not cancelling each other to give us zero resultant, but they are adding up to contribute to the total value, that is we obtain 4BIR in the I cap direction. So let us move to the next problem. A current of 10 ampere flows around a closed path in a circuit which is in the horizontal plane as shown in the figure. The circuit consists of 8 alternating arcs of radius 0.08 meter and 0.12 meter. Each arc subtends the same angle at the center. Find the magnetic field produced by this circuit at the center. The next one is an infinitely long straight wire carrying a current of 10 ampere is passing through the center of the above circuit vertically with the direction of the current being into the plane of the circuit. What is the force acting on the wire at the center due to the current in the circuit? What is the force acting on the arc AC and the straight segment CD due to the current at the center? So this one is a very interesting problem. So in order to begin with it, we first of all determine the value of magnetic field, which is also the part 1. So we are beginning with the working formula, which I have already mentioned, that B is equal to mu naught Ni upon 4 pi r into alpha, that is the angle which the arc is subtending. So in this case the question is saying that they are subtending the equal arcs. So if we consider that they are subtending the equal arc, so I can simply say that the larger circle is going to combine together to produce a semicircle, and the smaller ones are also going to combine together to produce semicircle. That is, each one is contributing to an angle of pi to constitute the entire loop. And hence I can say for the larger and the smaller loop, we are considering the radius being r1 and r2 respectively, where the question is calling us that r1 is equal to 0.08 meter and r2 is equal to 0.12 meter. So if the bigger loop is combining together to contribute for pi angle, so I can say that due to the bigger loop, we are writing v2, which is equal to mu naught I upon 4 pi. The radius is equal to 0.12 and the angle which it is subtending is pi. So it will cancel out. And similarly, for the smaller one, we write mu naught I upon 4 pi. The radius this time is 0.08 and it is also combining together to subtending an angle of pi, which we cancel out to obtain something like this. And since all of them are producing the magnetic field in such a way that the direction of magnetic field is directed outside the plane of the screen, that is directed outwards, so I can say that the two values must be added together to give us the net value of magnetic field. And hence we say that B net is going to be the sum of B1 plus B2, and it will be directed outside the plane of the screen. So we obtain from here by adding the two expressions which we obtained in the previous page, that is this one and this one. If we substitute the value of mu naught and the value of current, that is equal to 10 ampere, so I is equal to 10 ampere, we solve and obtain a value equal to 6.54 into 10 to the power minus 5 Tesla. So this is the value of magnetic field that we obtain, 6.54 into 10 to the power minus 5 Tesla, which is directed outwards. The next, if we read at the problem, it is stating that an infinitely long straight wire carrying a current of 10 ampere is passing through the center of the above circuit vertically with the direction of the current being into the plane of the circuit. What is the force acting on the wire at the center due to the current in the circuit? What is the force acting on the arc AC and the straight segment CD due to the current at the center? So if we consider this part, so the first part, the value is going to be 0. The force acting on the wire at the center is going to be 0 because it is carrying current. The current is basically directed into the plane of the circuit, and the value of magnetic field is coming out of the plane of the circuit, or out of the plane of the screen. So I can say that for the B part, the first portion, that is the force acting on the wire at the center, is going to be 0 because the angle between the external magnetic field produced due to uh, the arcs and the current carrying a wire is making an angle of 180 degree. So the value of ILB sine theta, that is the magnitude of force, will come out to be 0. The next one, we are calculating the force on the arc AC due to the current at the center. Now due to the current carrying wire which is infinitely large, we say that magnetic field due to infinitely large wire is given as mu naught I upon 2 pi r. So since it is calculating at AC, we are calling this distance as r1, which is equal to 0.08 meter. So this is the value of magnetic field. Now if we look at the diagram back again, on AC, we say that the direction of the magnetic field on any small segment is going to be tangential. So if the current carrying wire is directed into the plane of the screen, that is the current carrying wire is carrying current like this, then the magnetic field which it is going to produce is going to be in a tangential way at any point at a distance r1, is going to be something like this, with the direction of magnetic field B vector like this along any point which is in the radial direction, and hence the value of force on AC is also going to be 0. So force on AC is also going to be 0 because the direction of the magnetic field on any small segment will be tangential. Now in the next part we are calculating the force on segment CD. So in the next part we are calculating the force on the segment CD due to the current at the center. So let us calculate the force on segment CD. So if we look at the location of CD, then it is something like this. Now the CD is directed perpendicular to the value of magnetic field, but the problem is the magnetic field is variable along the length of CD, as the distance from center is continuously changing and it is varying from the closest distance being 0.08 to the farthest distance, which is equal to 0.12 meter. So in order to solve for this, at a distance x somewhere between CD, we are selecting a small patch of thickness dx. So I can show you somewhere here in this way, that we are selecting at a distance x a small patch dx on CD, where we will be calculating the value of force. So I am redrawing this diagram over here, that if this is the length segment CD and this is the center, so we are selecting at a distance x a patch dx where we will be calculating the force. So this small force can be designated as df, which is equal to I dx into b, where dx is the length of the small segment. So the current is 10 ampere dx into the value of magnetic field, since it is infinitely large wire. So we get mu naught I upon 2 pi x. So for this expression we obtain as 5 mu naught I upon pi into dx by x. So we are integrating from R1 to R2, that is 0.08 to 0.12. So we obtain this expression on integration, which is equal to 5 mu naught I. So value of I is equal to 10. So I write it as 5 mu naught into 10 upon pi. The value will be ln x, and then we will be putting R2 and R1. So we will obtain ln of 0.12 upon 0.08. Integration of 1 by x with respect to dx will be ln x, where the value of R2 and R1 is 0.12 and 0.08 respectively. And on solving this, we obtain 8.1 into 10 to the power minus 6 Newton. Now the next thing we are doing is we are finding out the direction of this force. So this is the magnitude of force which we have obtained. So if we calculate the direction of force, so over here I can say, if we go back to the previous diagram, we are seeing that the current in the wire CD will be in the upward direction. So the current in the wire CD is in the upward direction. So this is the direction of current which we have. And the direction of magnetic field, from the previous problem we have seen that the direction of magnetic field along any distance is going to be somewhat like this. So at this portion the direction of magnetic field was like this, B vector. So we say that B vector is somewhat like this. So if we use Fleming's left hand rule, so I can say that the force is directed downwards, that the force is directed downwards, or basically we can say that it is coming from this diagram into the plane of the screen, where we will be placing our fingers in such a way that our index finger is pointing in the direction of magnetic field, the middle finger is pointing in the direction of current carrying wire CD, and my thumb will be pointing into the plane of the screen. So we say that this is the value of magnitude of force which is acting on CD.